All right, so far we've been talking about different phases of matter and phase changes. For the next couple of concepts, we're going to solely be focusing on gases, and today we're going to be distinguishing between an ideal gas versus a real gas. So the first thing we need to go over, though, is something called kinetic molecular theory, or KMT. This is ideal gas behavior. This is a theory used to explain the behavior of gases in terms of their motion. Now, we already know that temperature is a measure of average kinetic energy, and that's directly proportional to the speed of the particles. So in other words, the faster the particles are moving, the higher the temperature goes. So here you can see in the picture, I have gas particles moving around. Heat is added. The particles then move faster because they've increased their kinetic energy, and thus the temperature is increased. Now, there's some major assumptions of kinetic molecular theory. These explain the qualities of what we consider an ideal gas, so a gas that behaves under ideal conditions and thus characteristics. The first one is that gas particles themselves have no volume. So the molecules and atoms of the gas essentially have no volume. There is so much space between the gas particles compared to the extremely tiny size of the particles themselves that the volume of the actual particles is insignificant. This is why gases can also be easily compressed because of all the space between them. So we often say that the volume of gas molecules is neglectable compared to the total volume occupied by the gas. So really when we say that a gas, say, is 2 liters, most of that volume is the space between particles, not the particles themselves. So students have sometimes a hard time kind of choosing that, especially in a multiple choice question, because it doesn't seem to make sense that molecules' volume would be neglectable. It's just that it's so tiny compared to the space between them. Another assumption of KMT is that the gas particles do not attract each other. Now again, this is under an ideal situation. There's no IMFs between gas particles. Now, in real life, all substances have some type of attractive forces, but in gases, the distance between the molecules are so great that we say that they don't come into play. So again, another assumption of an ideal gas is that these gas particles do not have any IMFs or attractive forces between them. Now, because of that, another assumption is that gas particles move in random, constant, straight line motion. So one thing we want to point out is that, again, this is for an ideal gas moving in these straight paths, and that's because there's no IMFs between these ideal gas particles. Now again, in real life, they tend to have more curved paths because they attract each other as they move close to one another. Another and last one that we're going to discuss is that the gas particles are perfectly elastic, meaning that they lose no energy when they collide with one another or with the walls of the container. Now, when two particles collide, they will transfer energy perfectly between them, but the overall energy is conserved. There's no energy that's lost to the environment. Obviously, the lower the concentration of gas, the fewer the collisions compared to a higher concentration with more collisions. All of those collisions in each of those cases, again, would be perfectly elastic. They would transfer energy between, but all energy would be conserved between those two atoms. Now, there are some problems for actual real gases fitting this kinetic molecular theory. Now remember, an ideal gas has no IMFs, their particles are neglectable, and so on. Now, real gases, the larger the molecules or atoms, the stronger the IMFs, so they're not going to fit that ideal gas theory. Particles that are moving slower, so those that are at a lower temperature, are subject to more IMFs. They're going to have more of an impact on each other and thus stray from kinetic molecular theory. Also, the smaller the containers means more collisions, so there's more chances for those collisions to not be elastic. So when do real gases actually follow kinetic molecular theory? What conditions are needed for a real gas to behave under these ideal characteristics? Well, the smaller the gas molecules, the more ideally it behaves. So if we're looking at our noble gases, helium and neon are going to be more ideal-like compared to something like argon or krypton. Okay, also the weaker the IMF, the more ideally it's going to behave. So gases with London dispersion forces, which are those that are nonpolar molecules, are going to behave most like an ideal gas would and follow KMT more closely. Now, gases with hydrogen bond attractions would behave least like an ideal gas because, again, the stronger the IMF, the less it's going to stray from kinetic molecular theory. And then this is a really important one. What conditions really are needed for a real gas for us to force it to try and be more ideal-like? Well, high temperatures and low pressures allow a real gas to be most like an ideal gas and follow that ideal behavior. To behave ideally, particles of the gas must be moving at a high speed and be far apart. So a high temperature and low pressure, which achieves that, basically minimizes IMFs between them, and thus then they'll follow those major assumptions of kinetic molecular theory. Real gases fail to exhibit ideal behavior if they're at the opposite conditions, at a low temperature and a high pressure. The low temperature means they're moving slower at a slower speed, and at the high pressure they're going to be really close together. So they're going to have bigger IMF and attractive forces between them, which then means then that they're going to stray from the ideal gas in KMT. They're not going to obey the gas laws completely. All right, so you should be walking away with having an ideal of what is an ideal gas, what characteristics those are, and also when a real gas can follow it and then stray from that. So just make sure you kind of straighten that out, reread your notes, and we'll go over this in class tomorrow.